So welcome everyone to the Spectral Geometry in the Cloud seminar. Today we have the pleasure of having Yevgeny Liokumovich, who will speak about parametric geometric inequalities and their applications. You have the stage.
Thank you so much for inviting me. Please feel free to interrupt me at any point and ask questions. I'm going to talk about some parametric versions of two very classical and important inequalities in geometry. So these are the parametric inequality and the coarea. These two kind of go into opposite directions. One can use isoperimetric inequality to feel k-dimensional cycles with k+1 dimensional chains of controlled size. One can use coarea inequality to chop up k-dimensional cycles into lower dimensional cycles of controlled size. So there's an interesting interplay between these two that we will explore. But let me start from the beginning. So let's focus on the isoperimetric inequality first. That's a very classical, ancient, one could say, result going back to almost 3,000 years ago when Queen Dido, according to Virgil's Aeneid, asked, well, she moved to what's modern Tunisia, and King Jarbas offered her some portion of land, but he didn't want to give her a lot of land, so he said how much you can cover with an ox's hide. And then she had an idea of cutting up the hide into tiny, tiny strips and then surrounding a lot of area with these tiny strips. And this way she got quite a bit of area and founded the city of Carthage. What's interesting is that Carthage was actually on the sea, so it was not a simple isoperimetric problem where you just do the circle, but you kind of had to solve an isoperimetric problem in the space with boundary. One could state the isoperimetric inequality in Rn in the following way, that the volume of a region bounded by a certain n-1 dimensional closed set is controlled in terms of the n-1 volume of the boundary. But the isoperimetric inequality that we will be interested today is slightly different one. So you can think about this one as an isoperimetric inequality for codimension 1 regions, right? So you cannot enclose more volume than what's given by this inequality, and the optimal way of doing that is when the boundary is a sphere. But what if instead of n-1 dimensional closed hypersurface, we have a smaller dimensional hypersurface? So we'll be interested in a situation where we're looking at a k-dimensional submanifold over n. So for example, we can think about a circle in R3. And then we would like to understand the relationship between the size of this closed curve and surfaces with that boundary, surfaces that it encloses. Now, of course, we can have very large surfaces, right? So you can have an extremely large surface with this boundary. You can make it as large as you want. So in this sense, there's no control between the size of the boundary and the size of the field. However, we may restate the question and ask, well, do we have control over the size of the smallest possible field? So we have this k-dimensional submanifold, and we would like to find a manifold with boundary that has this fixed boundary that has smallest possible volume, and whether we can control that smallest possible volume in terms of the size of this k-dimensional submanifold. So this is known as an isoperimetric inequality in higher dimension, and different versions of this inequality have been proved by Federer Fleming, Michael Simon, Almgren, Gromov, Wenger, and there's an interesting recent proof by Simon Brendel. And the statement is that you can indeed control the size of an optimal filling. So there exists some filling whose size is controlled in terms of the size of the boundary in this way. Fleming's initial proof gave a bound where this constant depends on the dimension of the ambient manifold, and Michaels and Simon gave a bound where this only depends on the dimension of the submanifold K. Hundren gave an optimum inequality in Rn, and Gromov and Wenger gave proofs of this inequality where the ambient space is actually infinite dimensional Banach space, and they needed that for some interesting applications in systolic geometry. So this inequality has many applications, so I mentioned some of them here. There's also in their paper, Michael and Simon use this inequality to prove a Poincare inequality on submanifolds in Rn. But Gromov used this type of inequality rather spectacularly to prove his systolic inequality. And then it also appears these types of inequalities also play a role in the study of scalar curvature. But today, I'm going to focus on the application of this inequality to the study of minimal surfaces, minimal submanifolds, which arise from Morse theory on the space of flat cycles. This will be the focus of today's talk. Are there any questions so far? So, this was an isoperimetric inequality in Rn. Now I'd like to focus on a slightly different kind of isoperimetric inequality, an isoperimetric inequality in a space of fixed diameter. So if you have a cube and you have some k-dimensional submanifold in there, one of the things you can do, the simplest thing that you can do probably, is to find a filling by just taking a cone. And so then the volume of the cone over C is then controlled up to a constant by R times the volume of n minus k-dimensional volume of Z, where R is the side length of this cube. Now, in general, this is not a good inequality if Z is small, right? So if Z is small, then if the volume of Z is much smaller than 1, then this linear inequality is much smaller than R. So if volume of Z is much smaller than R, then this is worse than the isoperimetric inequality where you get volume of K, C to the power of K plus 1. Then this is worse. But if volume of Z is very large compared to R, then this linear isoperimetric inequality will be better than the usual isoperimetric inequality in Rn. So basically, when you try to prove isoperimetric inequality in the Euclidean space, you kind of want to chop up your manifold into pieces whose volumes are comparable to the sizes of the box into which you chop up, right? And then in those boxes, you can just take the cones and do that. And the problem is if your submanifold has somehow very long fingers, which have very small volume, but large diameters, then taking the cone is bad. But if you want to understand the isoperimetric inequality for cycles of very large volume contained in something of small diameter, then, well, then it really depends on the kind of cycles we want to understand. So if you want to understand cycles which are with integer coefficients, then we can't really do better than the linear right? You can think about a circle a loop going around many, many times. And well, in order to fill that loop, there is nothing you can do except to take the cone over that. So linear inequality will be the best. But if you have mod 2 Z2 coefficients, then you can actually do much better than the linear isoperimetric inequality. And so let me illustrate that with just the simplest case where you have zero-dimensional cycle in a square. So you have many, many, many points. Well, one thing you can do is, of course, you can take a cone. You can pick a point and then take lines connecting all of these points to some single point. But the other thing you could do is you can cut up your cube or square into pieces. So say we have that the volume. So we take n approximately equal to the volume of Z squares. Right? And then in each QI, you can take a cone connecting points inside the points on the boundary. Then you can connect all of the points in the boundary by filling this cycle inside the boundary. The result will be a filling of volume filling tau with volume tau. Well, how can we control the volume tau? Well, first of all, we will have n different cubes, and in each cube we take this cone. So in other words, we're taking a cone of diameter of radius r, where r is 1 over square root of n. Yeah, that's the side length of each square. So we will have 1 over square root of n times volume of z. And then as we're filling the boundary of these points that are now in this one-dimensional skeleton of the subdivision, we have some chain which lies in the union of these boundaries of QIs. And well, because we're dealing with mod 2 cycles, the worst it can be is just the size of all the boundaries. And the size of all the boundaries is, so we have n squares, and well, the boundary is approximately, it's 4 times 1 over square root of n. So we have something like that. And so what we get is square something on the order of square root of n up to a constant, which is just volume of c to the power 1 over 2. And more generally, we can use these types of argument to produce tau for ck. We will produce a filling tau with volume of tau bounded by up to a constant by volume of z to the power of n minus k minus 1 for n minus k, where n is the ambient dimension and k is the dimension of the cycle. So in higher dimensions, we have to be a little bit more careful. Instead of just taking arbitrary cones, we use Tedder-Fleming projection from an average point, and then we push everything into the k+1 skeleton, and then we fill in the k+1 skeleton. And this is the inequality that we will obtain. And it's better than the linear inequality, and it's much better than the isoperimetric inequality with the usual powers. So this is going to be the optimal isoperimetric inequality when you have a large volume cycle in a cube. Are there any questions? So this is the type of isoperimetric inequality that we will be interested in. Now let us switch gears to coarea inequality. So the coarea inequality says that if you look at the integral from A to B of the volumes T, and that's just the integral of gradient f, the value of the gradient. So this inequality is very useful when you apply it to f distance function, and you want to find, you want to restrict this distance function to some submanifold in your space. So let me say more precisely what I mean. So suppose we have some region omega, and then we define let f be distance function for x to the bound of omega. Then suppose we have some k-dimensional submanifold. And then we can observe that the restriction, the gradient of the restriction of f to z is going to be less or equal than the gradient of f, right? So it's always faster to move in the ambient space than if you have to move constrained to a certain submanifold. And well, what does this mean for us? It means that if we consider the integral of, let's say, from 0 to sub r of volumes, a minus 1 dimensional volumes of intersection with of our z is f inverse t. Well, that's going to be less or equal than volume of z intersected with f inverse 0 to r. So if you're looking at level sets of a distance function from the boundary, and you integrate these volumes, k-1 volumes of this intersection, then they sum up to something which is controlled from above by the volume of your submanifold in that region. So in other words, what that means, that there exists some t in 0r such that k-1 volume of z intersect f inverse t is bounded by the volume of z over r. So because the sum of their volumes is controlled by above by this quantity, it means that on average we can find some value of t where the intersection will be controlled. So where inequality can be used to control the sizes of, to chop up our k-dimensional submanifold into k-1 dimensional subsets and control the sizes of these subsets on average. And this inequality holds not just for smooth submanifolds, but for k-dimensional cycles.
So may I ask a question? So here there is no constraint on this R, because I mean the shape of omega may be in such a way. So you stop at cut locus, or?
Right. Yes. So that's a good observation. So there is constraint on there is constraint on the size of R, but we don't necessarily have to. I mean, this argument still holds for.
Yeah, possibly because you're counting both sides the same thing. So probably
Right.
inequality still
Right.
holds. Yeah.
That's right. Yeah. So we can go all the way until the region is defined. Yeah.
Okay. Thanks.
Okay, so these are the two inequalities that I'd like to discuss today. And let me talk about the application that will use these two inequalities. where we will use this to inequalities. So, so I keep mentioning Lipschitz cycles, and the space that I'd like to work with is the space of k-dimensional cycles with the C2 coefficients on an n-dimensional manifold M. And you can think of this space as having elements Lipschitz cycles in the same way as we define singular cycles in the definition of singular homology. In the same way, you can define Lipschitz cycles with the additional assumption that the maps are not arbitrary continuous maps, but are Lipschitz maps. And then you can think of topology on the space to be defined by as follows. So it's known as the flat topology, where given two cycles, C1 and C2, their distance is the infimum over all chains, k+1 chains tau, such that the boundary of tau is C1 minus C2. So minimizing over all chains tau, this boundary. It's that. And then you can take the completion of the space, and that will be precisely the space of flat cycle, k-dimensional flat cycles on n manifold. Right. So this space was initially defined by Federer and Fleming with the aim of studying minimization problem and plateau problem, finding minimal submanifolds that correspond to minimizing area in the homology or homotopy class. And the key issue that this space solves is that in general, if you try to minimize area, you may end up with, if you try to control the domain of your surface, if you can try to control the topology of your surface in the minimization process, then the sequence can be highly regular. So in the limit, it can develop very large singularities. And so if you want to find a nice, smooth, or sufficiently regular limit, then you really want to allow the topology to change. And so what this is what this space allows. It allows, as you do minimization, the topology to jump at. You have a well-defined distance that you can measure, with which you can converge to manifolds of different topology. And Almgren took another step and used the space not just to find minimizers, but to develop Morse theory on this space. And so the idea of Morse theory is that instead of just finding minima of your function, you want to consider saddle points, higher Morse index critical points. So if this is my zk space, and then this is my function, for example, k-dimensional volume, then what I can do is I can consider certain non-contractible families of objects. So each point here in the space represents some sort of k-dimensional cycle, k-dimensional submanifold in my space. And then I can try to push this family down until it gets stuck at the critical point. So this way I should be able to find higher Morse index critical points of my functions, not just the minimizers, but something like closed geodesic on the 2 sphere, right? So this one does not minimize length in any homology or homotopy class, but if you consider it as part of a family of curves like that, then it minimizes the maximum in the sphere. And so exactly gives us the length corresponding to this critical value. Okay. So this theory has been used very successfully to obtain minimal hypersurfaces. So there are some results in like compact for compact manifolds and for non-compact manifolds too, with some additional assumptions, for example, like finite volume. And then it's been used for other functional to find not the volume functional, but some modified functional to find constant mean curvature and prescribed mean curvature hypersurfaces. So how exactly does the construction go? There is an interesting connection between this construction and these critical values and classical theory of eigenvalues of Laplacian. So we would like to find some non-trivial family corresponding to some n minus k cohomology class in the space of cycles. So this n minus k cohomology class is the one that precisely corresponds to sort of fibration or foliation of your manifolds with n minus k cycles. Right, so there's one that if you glue them together, if you glue this n minus k family of k cycles, then what you will obtain is precisely the fundamental n-dimensional cycle of your manifold. So, for example, like in the picture before, you can consider this family of cycles. And then this, if you take this one parameter family and you glue in small two chains connecting nearby one cycles in the family, then you will obtain a two cycle. And this two cycle will precisely represent the generator of n-dimensional homology. So in this way, you can define a certain canonical element of n minus k homology, and then you can start taking cup powers, and you can show that all of these cup powers will be non-trivial, and you can again try to minimize the maximum in these cohomology classes, and you should obtain a critical point, critical value as a result of that. So you're taking the infimum over the supremum over all possible non-trivial families here. All right, so let me comment on the connection to eigenvalues of Laplacian. So for the eigenvalues of Laplacian, we can define lambda p as infimum or supremum of the Rayleigh quotient. Okay, and so we can think of this functional as acting on Rp infinity, right? So if you fix some Hilbert space of functions, then we'll observe that this function is invariant under multiplication by a non-zero constant. So, if this is, we take this E of f, then E of f is equal to E of C of f. So then it descends to the space of lines in this Hilbert space. And so we identify f C of f. And so that's going to be an infinite projective space. And then, well, so the eigenvalues of the Laplacian then are just taking so we're taking the infimum over all k-dimensional, p-dimensional cohomology classes, non-trivial p-dimensional cohomology classes in the space Rp infinity. And each one will give us a certain critical value. Whereas you can think about Wp n minus 1 as kind of the same thing, where instead of taking infimum, supremum of this functional, you take infimum supremum of the volume of the zero set of your function. So you can think of your hypersurfaces as zero sets of your function. So there is an issue with regularity here, that it's not a good setup to prove regularity for cycles when you think about them as just zero sets of some function. to prove that by doing this type of minimization, you actually obtain a minimal hypersurface. But there is a way to kind of make it more rigorous. There is a level set approach using the Allen-Kahn equation, where you can sort of do something quite similar. And so my postdoc Akashdeep, for example, proved that the Allen-Kahn approach gives you the same critical, the same width values, the same spectrum as when you use the space of flat cycles. Okay, so why am I talking about this analogy with the linear spectrum? Because of the conjecture of Gromov that the asymptotic behavior of this width of its values, as in the case of eigenvalues of the Laplacian, should only depend on the volume and the dimension of the magnet, and not on other features of the geometry, exactly as the Weyl law for the eigenvalues of the Laplacian. So this result has been proved in some cases. So this Fernando, Marques, and Neves, we proved it for hypersurfaces on Riemannian manifolds. Then with Larry Guth, we proved the case for 1 cycles and 3 manifolds. And currently, my student Bruno Staffa is finishing the proof for 1 cycles in all dimensions. And a key difficulty in going from the case of hypersurfaces to the case of higher codimension is these two geometric inequalities, the parametric isoperimetric inequality and the parametric coarea inequality that I mentioned. So let me mention some applications of the Weyl law. So here, this Fernando and Andre used it to show that in dimensions between 3 and 7, for a generic Riemannian metric, the space of minimal hypersurfaces is dense in your manifold. So not only you have infinitely many, but they're kind of filling up the whole manifold. And then Fernando, Andre, and Antoine proved a stronger version that not only they fill up everything, but they fill up, but you can pick a subsequence so that they fill up in a way that approximates your volume form, so kind of in an equidistributed way, similar to some results for geodesics in negative curvature, which were obtained with very different methods. And then with Bruno Staffa, we extended the result from minimal hypersurfaces to stationary geodesic nets. So stationary geodesic nets are generalization of closed geodesics. The closed geodesic is a critical point of a map from a circle into a manifold M, and the stationary geodesic net is a critical point of a map from maybe some graph into M. So geometrically, they look like graphs where the edges are geodesic arcs, and this is maybe not a good picture because the angles are not right. So the correct angles should be something like that. The sums of outward tangent vectors at each vertex are 0. Right? So this is a critical point of the length function. And my students Shinze Li and Bruno Staffa proved the stronger equidistribution property for stationary geodesic nets, assuming that the Weyl law holds. So in particular, the result, now that Bruno extended the Weyl law for 1 cycles to all dimensions, now this result is for all dimensions. Okay. So let me now explain where the parametric inequalities come in the proof of the Weyl law. So there was a key step in the proof of the Weyl law where situation is much nicer in codimension 1 than in higher codimension. So given manifold M, we had to cut it up into little pieces and then map those pieces into Rn, connect them by small tubes together, with the purpose of constructing a very good, nearly optimal p-dimensional family of cycles in Rm. And so the idea is that there is a way of proving the Weyl law in Rn by sort of scaling things and tiling your domain with smaller copies of itself, which is not available for Riemannian manifolds. So we try to convert the problem of constructing the optimal p-parameter family in the manifold M to a problem of constructing an optimal family in Euclidean space. In Euclidean space, we can construct a nice p-parameter family of this set, and then we will map it back into our manifold. Of course, the mapping is not continuous on the boundaries. So this new family is not a family of cycles. This is just a family of chains with boundaries in this domains, and it's not even a continuous well, you could say that it is a continuous family of chains if you do this carefully, but the point is that it's not really a family of cycles. However, the abstraction to them being cycles is that they have boundaries in the boundaries of this domain. And so if we can fill in those gaps in a continuous manner, maybe somehow like that, then we will have constructed a p-family, and one can show that it's going to be a good p-family. If it corresponded to the correct non-trivial homology class in Rn, then this new family, after we continuously add chains to turn them into cycles, is going to be a good non-trivial PC bound, good family of cycles in there. So one can simplify this issue, one can zoom into this problem by just considering two domains. So say you have a nice family of cycles in here and a nice family of cycles in here, right? So you have a family of cycles in the cube Q1, and you have a family of cycles in the cube Q2. But what you'd like is a family of cycles in the union of Q1 and Q2. So these have to be relative cycles. They are only allowed to have boundary in the boundary of the union. But right now they have boundary on this interface, this common intersection of their boundaries. And so in the codimension 1 case, there's a way to glue in a chain here so that this family of chains changes continuously, and the whole thing is a relative cycle in the union of Q1 and Q2. And moreover, the mass of this chain is controlled by the mass of this whole side, right, of this portion, right? Because we're dealing with mod 2 cycles, the chain n-1 dimensional chain supported in this interface cannot have larger mass than the mass of the interface. However, if we are in higher codimension, then the picture looks different. So suppose we are looking at 2 cubes. So now we have a family of cycles here, and a family of cycles there. Now, in order to turn this into a family of relative cycles in the union, we need to somehow connect these endpoints, either to each other or to the boundary. But we have 2 problems. Well, the sizes of these green cycles are controlled, but the sizes of their boundaries are not controlled. In particular, you can imagine a lot of tiny tiny cycles here with very, very large boundary. So we don't really know what the boundary size is. And even if we knew what the boundary size is, we would have to somehow fill in this boundary in a way that is continuous as these cycles move. So one can break this problem into two parts. So parametrically control boundary of our cycles dt, where t belongs to some p-dimensional space. Control size boundary. And two, parametrically continuously fill in those boundaries by chains t of control size. So this precisely gives rise to a parametric coarea inequality, coarea, and this is going to be the isoperimetric inequality. Are there any questions so far? I think, Asma, I think you're
Okay,
muted.
sorry. May I ask a naive question? On the previous slide, when
Sure.
you project to or cover by patches and to Rn, so here, why you need, I mean, it seems that all of these patches in Rn is kind of independent. So why one is not enough? Because then the image. So what is the role of this tube in Rn, or why you connect these patches in Rn? Because apparently it seems that they are kind of in Rn also. You don't care about make them continuous, and then you map back to manifolds. So why one open
Right.
box is
So,
not enough?
So, so what's important is that we have an optimal family that sweeps out the union of these. If you pick optimal families that sweep out each one of them individually, and then you put them together, then this will not give you an optimal. This will not necessarily give you an optimal sweep out of the union.
And this tube, it kind of sees the intersection or the neighborhood of the patches on the manifold. So the way that you
Right. So this tube makes the topology a little bit easier. It's not essential. You can formulate this result if they're disjoint, but then you have to make sure that you pick the right topological class in the space of cycles, because then you have kind of disconnected. When you have disconnected domains, then it's the space of cycles, the topology of the space of cycles is a bit different than if you have a connected set.
Okay, thank you. Yeah, I think it
right, because then
clarifies.
you have distinct you have different connected components, and the important thing is that we have to pick a family that is optimal for the sweep out of the whole thing. So the restriction of that family to each region will not necessarily be an optimal sweep out of that region. So so what can we do? So let's start with the coarea inequality. Imagine that our family of cycles looks like it's very, very, very windy spiral. And then let's say we have just one parameter family. T. This be 0, 1. And then as t, so we start at z0, and as t goes from 0 to 1, then this windy part moves to the right. Now, for each individual ZT, we can use coarea inequality to slightly wiggle the boundary to make sure that the intersection is smooth. This is true even when this windy part gets close to the boundary. So if you're in a situation where it's kind of looks like that, we are like that, well, we can just move a little bit past this windy region, and then our intersection will be smooth. However, if we try to do this in a continuous manner, then we have a problem that, before this windy part hits the wall, we want to cut on one side of it. And then once it starts hitting the wall, well, we have to somehow jump over. So there is an inherent discontinuity here if we just want to wiggle the boundary by level sets of the distance function. At some point, we have to do a jump. There is no continuous way of doing that. However, we can do something more elaborate. Instead of just varying the boundary, we can try to add some stuff to our cycle. Right? So if we are in a situation where it looks something like that, well, we can start modifying the cycle here by adding some pieces, and then that can restrict, reduce the size of the boundary. If we can make sure that we add, that we can control the size of the pieces that we are adding. So the proof of parametric coarea inequality goes something like this. So for each individual cycle, so we have some complicated cycle, we can wiggle the boundary a little bit to control the size of the intersection, and then we can expand this region to the whole thing. Or alternatively, we can project onto somewhat smaller boundary to preserve continuity in the interior. So if we have a large dimensional p-parameter space, then we can start by doing this on the zero skeleton. We can pick a small triangulation of our parameter space, and we can do these types of cuts for each point in the zero skeleton of our parameter space. And so the result will be a collection of cycles which are the same cycles that we started with in the interior, but on the boundary, there are different portions that kind of appear and disappear. There's no continuity here on the boundary. And then the idea is to try to interpolate between different cycles corresponding to our zero skeleton by contracting their pieces in the boundary. And the difficulty is doing that in a way that controls their mass. If you are allowed to increase the mass of the boundary by something like 2 to the p, by some exponential factor in the number of parameter space, then it's not terribly difficult to do that. But in order to prove the Weyl law, we need to be very careful in how much the mass can grow. So this is the technical statement of the parametric coarea inequality conjecture. If you start with a family of cycles in an n cube, then we can decrease the size of the cube a little bit by some small r0, right? So we can go a little bit inside. And then we can modify our family to a family in here so that, well, here in the interior, it's the same thing that we had. But then we also add stuff here in the boundary that reduces the size of the boundary. So this is exactly like in the usual coarea inequality. And this is a term that's necessary because if you have a p-sweep out of your cube, and if you perturb your cycles so that they intersect nicely transversely at the boundary, then it has to be a p sweep out of the boundary too. Then the boundary of your the family given by the boundaries of your cycles will be a p sweep out of the boundary, and then it has to have at least this size. And the usual coarea inequality doesn't necessarily give you that. So we know that we will necessarily have this factor too. And then you also want to control the size by how much you increased the volume of your family. And this is the sort of factor, a reasonable factor that you should expect to get. So this is the parametric coarea inequality in the cube. And then let me also state the parametric isoperimetric inequality. So there is a version of it in the Euclidean space, which generalizes the Michael-Simon Federer-Fleming isoperimetric inequality. Instead of feeling just one k-dimensional submanifold, you want to continuously feel a p-parameter family of, in this case, a k-parameter family of submanifolds. And then there is a version for family of cycles in the cube. This is the one that you need to prove the Weyl law. And then you have this power n minus k minus 1 over n minus k that I explained in the beginning. Right. And so the status that this one is kind of pretty much open. So there are some sketches of how you can do this in low dimensions, but it hasn't really been written up. And this result has been proved for 1 cycles in 3 manifolds by Larry Guth and I, and more recently by my student Bruno Staffa for 1 cycles for 0 cycles actually in all dimensions. And there's an interesting connection between the parametric isoperimetric inequality and the coarea inequality is that if you have parametric coarea inequality, then you can use it to prove parametric isoperimetric inequality in the next dimension. So these 2 inequalities somehow go hand in hand. Yeah, I think this. Let me finish.
Okay. Thank you very much, Yevgeny, for your nice talk. So if there are any question or comments, you can unmute yourself. So maybe I start with a question. So you mentioned about the application of this Weyl law about that gives us density of existence and density of the minimal hypersurface or equidistribution of them. So
Yes.
What's the idea? Like how from Weyl law one get those? What's the bridge?
So the idea is that if we know that these WPs for p to the power of minus 1 over n, so this limit only depends on the volume of your manifold. That's constant. So if you pick a small region here and you make a small conformal perturbation that decreases the volume a little bit, and that means that you've changed the asymptotic. That these WPs, they are now going to a different limit. On the other hand, you know that each of these WPs corresponds to volumes of some minimal hypersurfaces in your magnet. So if you have that small perturbation of the metric, so if you have that, you don't have any minimal hypersurfaces passing through this small ball, and you don't have that for an open set of metrics, for a small open set of metrics, then somehow what happened is that when you did this conformal perturbation, you've changed the asymptotic of this sequence, but you didn't change the volumes of any of these minimal hypersurfaces. The minimal hypersurfaces somehow remain the same.
Okay.
And that gives you a contradiction.
Okay, thank you.
You must have, when you did this perturbation, because you changed the asymptotics, you must have also affected the volumes of minimal hypersurfaces that pass. So there must be some minimal hypersurface that passes through this.
And here the fact that this P it's asymptotic, P goes to infinity. So
Yes.
this argument is asymptotic argument.
Right.
Or
Yeah, so maybe more so more precisely, the argument is as follows. So generically, it's known that the set of minimal hypersurfaces is countable.
Mhm.
Or you could think about it as sort of just the observation that the set of singular values, the set of critical values has measure 0. So the set of volumes of minimal hypersurfaces has measure 0. However, if you have a family of perturbations, GT, so that the volume GT is in some interval, right, between maybe G minus V minus epsilon to V. So this is your initial volume. And so as you're starting conformally varying the metric, the volumes start to vary in some interval. And then that then gives you that somehow you have a family of accountable. So now if no minimal hypersurface passes through this interval, then it's the same fixed countable family of hypersurfaces. But somehow their asymptotics changes in an interval, right? So the volumes sum up to something that's continuously changing in an interval. So the volumes then cannot have measure 0.
Okay, thank you.
Does it make sense?
Yeah. So, any other question or comments? So, if not, let's thank Yevgeny again. Thank you very much. And so we resume next week with the talk by Grigory Rosenblum. So he will talk about Weyl asymptotic for Poincaré Steklov eigenvalue in a domain with Lipschitz boundary. So thank you all, and see you next week.
Thank you. Bye-bye.
Thank you.
Thank you.